Hello, everyone. Am I audible? Okay. Thank you. Thank you for inviting. Thanks to the team at Carbfix. I'll be talking about some of the work we have been doing in this space. So I'm one of the two Vikrams who is going to be on the agenda for the 2 days. So the first one for today. I'll be talking more on the mineralization potential of the Deccan basalts. So I represent the DST's sponsored National Center of Excellence in CCUS at IIT Bombay in India. And this is a national center, the first such national center of excellence, in which does a lot of R&D and then a lot of policy advocacy to the government of India. We are working on carbon capture, utilization, sequestration, and then there are the cross-cutting systems as well that we are working on. Like any other diversity in India, we have a lot of geological diversity. We have all the kinds of reservoirs where we kind of look for storing carbon dioxide that are there available conventionally. But then what we are trying to focus is on the basalts out here. So what is the total theoretical potential of storing carbon dioxide in India? We have been hearing about millions of gigatons around the world. So what is the number that has been done for India? If you look at the conventional oil and gas systems, we have 3.4 to 3.7 gigatons of CO2 storage potential. We have 26 sedimentary basins, of which 7 of them are producing oil and gas. But then there are saline aquifers, both onshore and offshore of India. So a total of 291 gigatons in these saline aquifer formations. That's only estimated at 1% storage efficiency. So you can imagine it could be much more than this when it gets into real action. And for basalt formations, the potential to store is around 97 to 316 gigatons. So this number is wide because we have not done any pilot injections. So a lot of studies need to be done to kind of get to the more closer estimation. So you can see this wide number itself is a motivation for researchers like myself to be working on this. So collectively, we have nearly 400 to 600 gigatons of CO2 storage potential in India. To give you an estimate, India emits roughly around 2.8 gigatons of carbon dioxide annually. So all across the country, there's a wider distribution of these locations for storing carbon dioxide. And definitely, we can look into what can be done in terms of storage in the basaltic formations. So this is what you see here in green is representing the basalts in India. So most of them are in the Deccan basalts that are on the western and west central part of the country. And there's something called Rajmahal volcanics on the eastern part of the country. If you look at the Deccan basalts, it's around 500,000 square kilometers of exposures. And if you take the average 1 kilometer thickness, you have almost 500,000 cubic meter of basalt that is available. On the western side, it's deeper, so we have depths going up to 6 kilometers, while on the eastern side, it's closer to the surface. So pretty much a distribution of basalts exists across the country, and large number of them have been studied. You could see that with our partner organization, the Geological Survey of India, we have available around 600 points chemical data, petrographic thin sections of 300 samples, and then section measurements across 50 of them. And this is a picture that you're seeing on the right is indicating the way it is distributed from the surface. We have big, beautiful hills out there in the western part of the country. This is indicating the topographic map of the Deccan basalts. Almost the lower Sahyadri formation, as we call it, is divided into the lower and the upper formations. The lower formations are Salher, Ratangad, and Indrayani. So you can see on the western side the degree sheets, as we call them, the topo sheets, and covering nearly 100,000 square kilometers, and there are several points of which 200 points from where the samples were collected and analyzed for this purpose. You could see that it's very difficult to kind of get the surface samples, but then the team at GSI and at IIT Bombay have been consistently working towards it. The morphology of flow of the Deccan traps is quite interesting. It's again, of quite a diversity in terms of distribution of these lava. So what we call as the Pahoe lava, the R lava, and then there's a compound lava. Then there are these basal clinkers in place in between. And then there are the location of these glassy lines, which are indication of different situations of eruptions. And what we try to understand is the disposition of the fractures, the porosity, permeability, and how that's going to affect when we are going to inject carbon dioxide in the subsurface. So the surface analogy is going to be extrapolated when we are trying to understand for the subsurface, because very limited data exists in terms of seismics and as well as well-bore data for this. So once we go to the field, we collect the samples, but we have also done some dedicated deep drillings. So we have got samples from up to near surface to 3 kilometers deep, and they have all been brought into the lab and analyzed. So at IIT Bombay, have a state-of-art research laboratory where we continue to do the analysis on these rocks. What you're seeing in the top center are the different reactors where we subject the subsurface conditions. So we create the pressure condition, we create the temperature conditions, and inject carbon dioxide along with water that is present, and we try to see the rate at which the reactions are going to happen. So again, the laboratory where these conditions are created, we subject the rock to deformation in a saturated condition and try to see what happens eventually when we inject CO2 in the subsurface. And these become inputs to the numerical models that we are trying to build. Getting closer into these samples, this is how the basalt samples would look like in the photomicrographs of the collected samples. So largely what I want to emphasize that we have quite a diversity of these basalts that are present, rich in the plagioclase, pyroxenes, and olivines. So we did all the sampling of around 200 samples and found out 3 major classes of basalt that we are looking at: the andesitic basalt, the tholeiitic basalt, and the picritic basalts. So these 3 different composition in terms of their calcium and magnesium ratios, and also the iron composition that is present, and see which one is going to react faster and yield the results that are favorable in terms of doing carbon sequestration. So with these experiments, we found some of the evidences of dissolution using the EPMA analysis and the ICP-AES analysis. So you can see that there are cracks initially, and then there are depressions. So basically, a lot of minerals have dissolved in the process of doing the experiments, and consistently the concentration of the cations is increasing in the water that is present. So that's basically indicating the dissolution of minerals. But we are also getting evidences of precipitation. Right there in the center, you have this figure of the reaction chamber. You could see very fine crystals of this calcite, which is deposited all around this at the interface between CO2 and water, and that's where the maximum reaction is happening. Through the image analysis, we are getting to see where the magnesite is, where the silica is, and then we have the calcium magnesium carbonate that is also present. Further to this, on the evidence of precipitation, we have done the thermogravimetric analysis and the XRDs, so classically trying to simplest ways of understanding which minerals were really formed. So from the decomposition curve at temperatures, we are inferring that these are calcium and magnesium carbonates that were formed, which were not there reported earlier. Further to this, we do understand there will be rock mechanical changes, which will have implications when we are doing the carbon dioxide sequestration. So we get these samples, we subject it to deformation conditions in supercritical carbon dioxide that is getting injected, which is above 7.38 megapascals and 31.1 degrees Celsius, so closer to around 800 meters depth. And therefore, we do this characterization and incorporate them into the numerical model. So this is how the simulation work has been initiated, and we're looking to the schemes for injection. So when we go for earlier injection, a huff and puff method, and then kind of relax, and then inject again. And then we have methods of doing continuous injection, both carbonated water as well as supercritical carbon dioxide. So these are some of the preliminary state of understanding that we have. What we realized largely is that the carbonated water solution is indeed reacting faster based on some of the experiments. So further to that, what we also have developed is a method which actually accelerates the dissolution of carbon dioxide in water. So it's basically a biomimetic catalyst, which kind of mimics the action of carbonic anhydrase. That's an enzyme in our body. So as we know that we inhale air, but we exhale carbon dioxide. So there's something in the body which is converting carbon dioxide into its ionic form, which is carbonate and bicarbonate, and they're really converting it back as we are exhaling. So mimicking the process of the carbonic anhydrase is what we are doing. We have an innovative synthetic patented catalyst, and based on that, we also have launched our own startup called Urja Novak Private Limited, along with our partners Abitec and Ingenero. So in this small reactor that you can see in the center, we are capturing almost 300 kgs of carbon dioxide in this process, and then we are after the capture of CO2 in this water, we are deriving the cations from basalts and making them react to form calcium carbonate. And incidentally, on the right-hand side, bottom, you can see there are packets of calcium carbonate which are from the synthesized, from capturing CO2 from air, and the calcium that is derived from basalts. So all in all, we also see the potential for having a valuable chemical product. It's not just CCS and CDR, but also CCU element can come if you want a pure calcium carbonate, which can also be readily used in a process. So I think the concept that we came up with to do CO2 storage in basalts is also translating something which has a great amount, CAGR for the commercial deployment through Urja Novak. Finally, as a national center, we are also a think tank for the government. We are providing a lot of support to different ministries. We launched the CCUS implementation task forces, and also through different ministries, we launched some reports. And finally, if you see in the bottom, we are developing the CCUS mission for India, for the government of India, and all the knowledge that we have developed so far are getting readily incorporated into it. Large number of roadmaps have been written in the last 2-3 years since the Honorable Prime Minister announced net zero by 2070. And we do understand that onboarding India is very important for achieving net zero for the world. And that's where the activities here become very important. I must acknowledge the partnership with US DOE, through which we written this CCUS handbook for policymakers, and consistent interaction that is happening. And similarly, now we acknowledge the partnership with Carbfix that we are trying to build on, and so on. Finally, the way forward that we realize is that we need to develop a robust monitoring system specific to the field terrains that we are having. So the lower as well as the upper geological formations of the Deccan basalts need to be studied. The simulations have to be very, very, again, robust based on the reaction kinetics, the mineral chemistry, and the petrophysical properties. Finally, one more element I must inform here, that we are trying to do a pilot injection CO2 project for monitoring, and that project is also in final stages of discussions. And eventually, we want to expand from the work that we are doing near Mumbai, which is the western part of India, to a little east central Deccan traps as well. Thank you so much for your kind attention.